Hello students. So in this class we will see next 10 questions from the specimen paper of ISC Physics. Okay, so this is Sovik Das and I have come here to discuss next 10 questions. Okay, with all of you. So our first question is this, that is question number 11. So here it is given three charges Q1, Q2, Q3, as you can see here Q1, Q2, Q3. Their values are given 3 microfarad, 4 microfarad and minus 7 microfarad. Okay. Placed on the circumference radius radius 1 meter. Yes. As in, what is the value of charge Q4? What will be the value of charge Q4 placed on the same circle if the potential at the center is 0? So potential at center, what will be the potential at center C? Potential at center will be due to all the four charges. Okay, now all the charges are at same distance, that is 1 meter. Okay, all the charges are at same distance, 1 meter, 1 meter, 1 meter. And our formula of potential is K Q1 by R. Okay, for four charges potential is a scalar quantity, so we have to add simply. Okay, K Q3 by R plus K Q4 by R. Now VC is 0. Potential at center is, okay, here it is missing something. What is the value of charge Q4 placed on the same circle if the potential at center is 0? Okay, so left side is 0. Right side, if we take common K by R, then it is Q1 plus Q2 plus Q3 plus Q4. So this part will not be there. Okay, this part will go to the left side, it will be 0. So sum of four charges should be 0. So 3 plus 4 minus 7 plus Q4 equal to 0. So 3 plus 4 7 cancel out, so this is 0. So Q4 will be 0. So correct answer is D. Okay. Our next question number 12. Yes, question number 12. Three equal charges 5 microcoulomb each are placed at the three vertices of an equilateral triangle of side 5 cm. The electrostatic potential energy of the system. So three charges, okay, like this triangle suppose, okay, here one charge, here another charge, here another charge, three charges. Their values are same, 5 microcoulomb. Okay, so in case of potential energy of a number of charges, we have to find the combination of two charges, and we have to add each potential energy. So total potential energy will be three combinations are here. This is one combination, suppose first combination, this is second combination, and this is third combination. So U equal to U1 plus U2 plus U3. Here the important thing is K is constant, that is 9 into 10 to the power 9. Okay, this is constant. Now Q1 Q2, formula of potential energy, U equal to K Q1 Q2 by R. Now look, Q1 Q2 same for first, for second this is Q1, this is Q2, for third this is Q1, this is Q2, so their values are same. So for one potential energy it will be K Q into Q, so Q square by R is the length of the side, so length is also same for all the three, U1, U2, U3. So basically we are getting U1 equal to U2 equal to U3. That means if we multiply this quantity by 3, we will get our answer. So 3 into 9 into 10 to the power 9 into Q square means 5 microcoulomb 10 to the power minus 6 whole square by R means 5 centimeter 10 to the power minus 2. Okay. Use your calculator, you can use your calculator in the board exam. So 3 into 9 into 10 to the power 9 into 5 square 25 into 10 to the power minus 12, right, equal to by 5 by 10 to the power minus 2. So we are getting answer 13.5. Okay, 13.5 joule. So our correct answer is here this. Fine. Going to next question. Our next question is question number 13 from capacitor, combination of capacitor. C1, C2, C3 are given. Okay, 3, 6 and 10 connected to 50 volt battery showing in the figure. The equivalent capacitance of the circuit between A and B. So equivalent capacitance between A and B. So here this is a mixed combination. Okay, for mixed combination we have to find the smallest part. This is the smallest part, and they are in series here. Okay, so 1 by CS, series combination means reciprocal. So 1 by 3 plus 1 by 6. So we are getting 6, 3 2s are 6 plus 1, that is 3 by 6, 3 by 6 means half. So CS we are getting 2. And CS, this CS and C3, these two are in parallel now. So parallel means simple addition. So 2 plus 10, 12 microfarad is the equivalent capacitance. So correct option will be either A or C. Okay. Now in the question is charge on C1. Okay, charge on C1. Now C1, C2 are in series. So charge on C1 and charge on C2 will be same. But C3 is in parallel. So here charge can be different. Okay. So for finding charge, we will take that part, that series part, okay, in which C1 is present. So C1 is present only in the upper part. Okay. So we'll take this part. Lower part is not required here. Okay, because this combination is parallel combination. With C1, C2, C3 is in parallel. Okay. In parallel combination, potential difference will be same. Okay, same potential difference across them. So to find charge on C1, we need C1 and C2. This line we need. Okay, A to B, this line where C1 and C2 present, this line we need. In this case, in series combination, we have to find equivalent, and we got it 2 microfarad. Okay. Now across this combination, C1 and C2 series combination, potential is 50 volt. So the charge will be Q equal to CS into V. CS is 2 into 50. That means 100 microcoulomb. Here it will be microcoulomb. Okay. Here it will be microcoulomb. All the options will be microcoulomb. Yes. 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 Fine. So for that reason, correct option is C. Correct option is C. If you are asked to find the charge on C3, then only this route we took. Okay, this route we would take. This route A to B. Here C is 10, okay, and 50. So 50 into 10, okay, that means 500 microcoulomb. Fine. Okay. Going to question number 14. Question number 14 is this, a very short question. A substance behaves like a magnet only if there are. A substance behave like magnet. Okay, magnet means we need current carrying loop, because current carrying loop behaves like magnet. Okay, bar magnet, current carrying loop. We need current carrying loop. Okay, whenever current is flowing in a loop, then here we can consider one bar magnet, right? Here we can consider at the center, you can consider one bar magnet like this. Okay, like this. Suppose current is flowing in this way, so here we can consider one bar magnet. Okay, we can consider one bar magnet. So at least some tiny current loops within the magnet should be there. Okay, which substance is behaving like a magnet. Question number 15. Question number 15 is this. Yes, this question is also a good question. Current is 16 ampere. Current is flowing in this way, then through this circle. Okay, then again upper half of the infinite wire. Radius 10 centimeter. Okay, radius 10 centimeter. At the center, what will be the magnetic field? So at the center, magnetic field, net magnetic field will come from two parts. One is B wire, okay, and another is B circle. What about the direction? Now due to B wire, you can consider these two parts together, and you can consider this wire as an infinite wire. For infinite wire, the point is on this side, right side. Suppose the point is P on the right side. On the right side of the wire, magnetic field enters like this. Magnetic field enters, right? Entering. So due to where magnetic field enters means cross. Now due to circle, just these four fingers, curl these four fingers along the current direction in circle. Okay, and this thumb will give you the magnetic field. So if you curl these four fingers along the current direction in the loop, then this thumb is coming towards you. That means perpendicularly outward. So here dot. Okay, that means opposite direction. So net magnetic field will be difference. Okay, now B where means mu 0 I by 2 pi r. Okay, because this distance is same, radius. And circle means mu 0 I by 2 r. Okay, Now which one will be bigger? Here pi is there in the denominator, that means more than 1 is there in the denominator. Here pi is not there, so this term will be bigger, right? So if we take common mu 0 I by 2r, mu 0 I by 2r, okay, 1 minus 1 by pi, this quantity will be bigger, so this one I have written first. Now mu 0 means 4 pi 10 to the power minus 7, current is given 16, 2 r is given 10 centimeter means 0.1 meter, 1 minus 1 by pi. After that use your calculator, okay, for finding 1 minus 1 by pi. So 1 by pi you will get 0.318, then 1 minus, so 0.68. So this quantity will give us 0.68, almost 0.68, yes, okay. So 0.68, okay, into 4 into pi into 16 is the current, into 10 to the power minus 7 equal to by 2 by 0.1. So we are getting 6.85 into 10 to the power minus 5, okay. So we are getting here 6.85 into 10 to the power minus 5 Tesla. So correct option is B. If you are asked about the direction will be circle 1 is the bigger, right? B circle is bigger than B where, okay. Now B circle is coming perpendicularly outward, so direction will be perpendicularly outward, okay, direction will be perpendicularly outward. Fine, this is the calculative question, okay. Now question number 16 is this, yes, this is easy question. Here you have to find this current you have to find, main current. So if we take these 2 points, okay, as A and B, then at point A current will get divided. Suppose here I1 and through this I2. Now this I2 will go through this 60 ohm and this 60 ohm also, okay. That means this one and this one are in series, same current is flowing, so series. So for this RS it will be 60 plus 60, 120. Now current got divided in this path, A to B direct path, this one and this path, okay, current got divided. That means this 60 ohm is in parallel with this combination, right, with this combination it is in parallel. So finally 1 by Rp equal to 1 by 120 plus 1 by 60. So we are getting 120 is the LCM, so 1 plus 2, that means 3 by 120, that means 1 by 40. So Rp will be 40 ohm. Now what about the main current? I equal to EMF 4 by resistance 40, that means 1 by 10 ampere. So our correct option is C, okay, correct option is C. Going to next question number 17. Yes, question number 17. Cell of EMF E. External resistance R. Potential difference across the cell is V. Internal resistance expression you have to write. Okay, so this is one cell. This is internal resistance, and this is one external resistance. Okay, so external resistance R, internal resistance small r, EMF E, and potential difference across the cell, okay, across the cell is V. Now if you look at this potential difference across the cell, the same potential difference will come across this resistance also, okay, same potential difference will come across the resistance. Suppose current is I, then what about the potential difference? We can write I into R, we can write, because there is only one resistance, okay, only one resistance, so same potential difference will come across that resistance also. Now I means what? I means EMF by total resistance R plus smaller, because this R and smaller are in series, same current will flow, okay, same current will flow into capital R. Okay, now we have to find the expression for small r. We have to find the expression for small r. Okay, so cross multiply on this side V. So V into R plus V into small r equal to E into R. Now this VR, take it to this side, so it will be V small r equal to E minus V into capital R. So what about small r? E minus V by V into R. So our correct option is B. Correct option is B. Okay, fine. Question number 18. Yes, question number 18 is this. This is also easy question. Just you have to keep the concept of KCL, Kirchhoff's current loop. Okay. So electric current I means this one we have to find, this one. So this is one junction where 4 ampere and 2 amperes are coming and flowing through this part. So through this part the current will be 4 plus 2, that is 6 ampere. Okay. Now come to this junction. Here 1 ampere is going in this way. So the remaining part will come through this. Okay. Through this part current will be how much? Current will be 5 ampere. Okay. Through this part. Now come to this junction, final junction. Here 1.3 is going in this direction and remaining part will go through this part, that is I. That means I plus 1.3 will be the entire current 5 because 5 is coming to this junction. So I will be 5 minus 1.3. Okay. So we are getting how much? 3.7, right? 3.7 ampere. Okay. This type of question very, very important. Just you have to keep the concept of KCL, Kirchhoff's current law, or Kirchhoff's current law. So option B is the correct option. Fine. Going to next question, question number 19. Yes, this is question number 19. Parallel combination of cell. Okay, n identical cells, each of EMF E, internal resistance R, external resistance capital R. Okay, so suppose this is cell, internal resistance, this is another cell, internal resistance, all are identical. So in this way, this and their nth number. Okay, nth number. So here EMF E R, this one also EMF E R, this one also EMF E R. Okay. Now when the cells are in parallel and the EMF of all the cells are same, okay, then equivalent EMF E equivalent will be equal to EMF of one cell. So here what is the special case? Special case is EMF of all the cells connected in parallel combination should be same. So the main point is EMF of all cells connected in parallel, okay, connected in parallel should be same. Okay, internal resistances may be different or same, but EMF should be same. Then only equivalent EMF we can tell EMF of one cell. Okay. Now what about the equivalent internal resistance? 1 by R equivalent. Now all resistances, internal resistances are connected in parallel. So 1 by R plus 1 by R plus dot dot dot. So in this way we will get N by R. So ultimately we will get R equivalent equal to R by N. And external resistance is there. Okay, external resistance R is there. Now this external resistance and equivalent internal resistance, they are in series. Okay, so R equivalent finally will be R plus R by N. That means if you take the LCM, then it will be NR plus small r by N. Okay. Now current in the resistance, this current through the main resistance I, so current will be I equal to equivalent EMF, that is E by N capital R plus small r by N. Now this N will go up, so it will be NE by N capital R plus small r. Okay, so our correct option is this. So here keep in mind this point, EMF of all the cells should be same which are connected in parallel, then only we can tell equivalent EMF equal to EMF of one cell. Internal resistances may be different. Here it is given internal resistances are same, okay, to make the questions easy. Okay, going to next question, question number 20. Yes, this is question number 20. This is one potentiometer circuit. Okay, we are comparing two cells E1 and E2, where E2 is greater than E1. E2 is greater than E1. Null point is at C when galvanometer is connected to E1. Okay, as shown in figure, null point is at C when it is connected to E1. Okay. Now the question is, when the galvanometer is connected to E2, the null point will be. Now here you need to have the concept of principle of potentiometer, which is equal to potential difference, okay, is directly proportional to the length between the 2 points on the potentiometer wire. Okay, here one point is here, okay, one point is here, and this is another point. So for E1 this is the length, for E1 this is the length. Now potential difference is directly proportional to this length from a point to another point, okay. The distance between 2 points, one point is a, another point is the other point on the wire, okay. Now as E2 is greater than E1, so obviously the length required to balance that EMF E2 should be more than E1, okay. Suppose L2, so L2 should be more than L1, okay. Now this one is L1. Now L2 should be more means if we connect this point with a galvanometer, then this point will come any other point, any point on the right side of C, okay, any point on the right side of C, because L2 is more than L1. Distances are measured from this point, okay, distances are measured from this point. So L2 should be more than L1 because E2 is greater than E1, okay. So here correct option is this, okay. So this is all for today. I hope you have enjoyed. So this is Sovik Das signing off. Keep watching. Thank you everyone.